Albert Einstein wasn't afraid to venture beyond the safe harbors of established physics. He believed that even the most outlandish claims deserved a fair hearing and, where possible, an experimental check. Here's a guided tour through the most controversial ideas he tested or seriously engaged with, and what he ultimately concluded. Orgone energy, Wilhelm Reich. Question: could a mysterious life force be captured in a wooden box? Answer: in early 1941, Einstein measured temperature differences inside Reich's Orgone accumulator and found that simple convection and insulation explained the heat buildup. No new energy was detected. Reich's Orgone hypothesis was effectively laid to rest by good old-fashioned thermodynamics. The ether revisited. Einstein blew away the 19th century mechanical ether with special relativity in 1905, but by 1920 he reintroduced a relativistic ether in his general theory of gravity. This wasn't a substance you could breeze through, but the dynamic space-time fabric itself, endowed with physical reality yet devoid of the rigid, undetectable aether of Lorentz and Michelson. Unified field theory, Einstein's own quest. Consumed by the dream of merging gravity and electromagnetism, Einstein spent decades chasing a deterministic framework that excluded quantum chance. No experiment ever confirmed his proposals, but his vision of a unified geometry influenced later pursuits in string theory and modern attempts at quantum gravity. EPR, paradox and quantum non-locality. Question: is quantum mechanics complete, or do spooky correlations hint at a deeper reality? Answer: together with Podolsky and Rosen in 1935, Einstein crafted the EPR thought experiment to challenge entanglement. That challenge sparked John Bell's work and a half-century of experiments, ultimately affirming quantum non-locality, even if Einstein remained uneasy with the implications. Wormholes, Einstein-Rosen bridge. In collaboration with Nathan Rosen, Einstein found solutions to his own field equations that connected two space-time regions via a bridge. While he dismissed them as unphysical curiosities, today, Einstein-Rosen bridges are central to debates on black holes and quantum information. Teleparallel gravity. Einstein once explored a gravity model based on torsion rather than curvature. He eventually abandoned it, but modern theorists occasionally revive teleparallelism in attempts to unify gravity with the other forces. Tired light hypothesis. Before Edwin Hubble's expanding universe became dogma, Fritz Zwicky suggested light might lose energy and redden over cosmic distances without expansion. Einstein considered this possibility, but in light of mounting astronomical evidence, sided with cosmic expansion and relegated tired light to the dustbin of discarded ideas. Static universe and the cosmological constant. To force his equations into a static cosmos in 1917, Einstein introduced L. When Hubble's observations revealed a dynamic universe, Einstein called it his greatest blunder. Ironically, L resurged decades later as dark energy, vindicating the once spurned term, though not Einstein's original reasoning, psychic energy and cosmic vitalism. Einstein corresponded with spiritualists and entertained discussions of a universal life force, but he never let metaphysics override empirical evidence. Mystical claims found no refuge in his physics. They remained interesting philosophically, but scientifically untenable. 0 point and vacuum energy. The concept of vacuum fluctuations intrigued Einstein, who pondered their thermodynamic consequences. He didn't reject 0 point energy. In fact, his early work laid groundwork for later quantum field theories, though he lacked the tools to develop it fully himself. Determinism versus quantum indeterminacy. God does not play dice, Einstein insisted, arguing that quantum mechanics must be incomplete. Though experiments ultimately upheld quantum randomness, Einstein's challenge spurred deeper inquiries into hidden variable theories and the foundations of quantum reality. Mesmerism and life energy concepts. Occasionally, Einstein referenced notions like prana or chi in letters, but he treated them as metaphors. No laboratory tests, no experimental embrace. In his view, such concepts lack the falsifiability required of genuine science. Einstein viewed science not merely as a method for cataloging experimental facts, but as a conceptual endeavor to unify nature under elegant principles. He was deeply skeptical of mainstream consensus when it conflicted with his notions of realism, determinism, or logical completeness. For this reason, he often entertained ideas that were unpopular or speculative if they seemed to promise deeper insight. His guiding criterion was internal consistency, not social acceptance. This philosophical commitment explains his repeated engagement with ideas on the margins of orthodoxy. Einstein supported early criticisms of quantum mechanics, not because he opposed its success, but because he felt it was philosophically incomplete. It's like a detective investigating the overlooked suspect. Not because it's probable, but because it's plausible and unexplained. In 1941, Albert Einstein personally tested Wilhelm Reich's Orgone accumulator, a device Reich claimed could harness a universal life energy. Einstein measured temperature differences inside and outside the box over several days in his Princeton home. He found that the warming effect was due to conventional convection currents and insulation, not any unknown energy. Although skeptical from the start, Einstein gave Reich's idea the dignity of empirical. His final report rejected the concept outright as physically unfounded. Einstein's letters from February 1941 document how covering and uncovering the box changed its internal temperature, fully explainable by airflow. It's like realizing a healing crystal works only because it was left in the sun. Although Einstein discarded the 19th century mechanical ether in special relativity, he later introduced a redefined version in general relativity. In a 1920 lecture, he stated that space must have physical qualities to carry gravitational and electromagnetic fields. This ether was not a material substance, but a structured field, a conceptual shift that retained the idea of a medium without returning to pre-relativistic physics. Einstein argued that denying space any physical properties left field theories incomplete. The idea anticipated modern notions of the quantum vacuum and space-time fabric. In his Ether and the Theory of Relativity lecture, Einstein said, "According to general relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. It's like saying silence isn't emptiness, it's the medium through which meaning travels." Einstein spent the final 3 decades of his life trying to unify gravity and electromagnetism into a single field theory. This pursuit was viewed as fringe by mid-century physicists who were focused on quantum mechanics and the emerging Standard Model. Einstein rejected probabilistic quantum mechanics and pursued purely geometric, deterministic models. He developed numerous variants involving higher dimensions, asymmetric metrics, and differential geometry. Although none matched experiments, these efforts laid a conceptual foundation for later unified theories like string theory. In 1950, Einstein published a paper in Scientific American proposing a non-symmetric field theory, which attracted little interest at the time. It's like trying to write one equation that describes both thunderstorms and symphonies. Einstein seriously explored Kaluza's 5-dimensional theory, which combined gravity and electromagnetism through an added spatial dimension. Though mathematically elegant, the idea lacked experimental validation and seemed disconnected from physical reality in the 1930s. Einstein co-authored refinements to allow a variable 5th dimension, hoping to build a pathway to unification. He was one of the few physicists of his time to take the model seriously. The theory would later gain relevance in string theory and modern unification attempts. In 1938, Einstein and Bergman published a modified version of Kaluza's theory in Annals of Mathematics, expanding its dynamic potential. It's like proposing that the universe is a 3D shadow of a 5D sculpture we cannot see. Einstein explored teleparallelism in 1928 as an alternative to curved spacetime, using torsion instead of curvature to explain gravity. This model replaced the geometric bending of space with distant parallelism, aiming to unite gravitation and electromagnetism. Though mathematically innovative, the theory did not improve on general relativity's predictions or lead to successful unification. After publishing several papers, Einstein abandoned the approach. Though modern researchers still explore its extensions, it remains a valuable case study in alternative geometries of gravity. Einstein's introduction of tetrads in teleparallel theory has since influenced gauge theories and modern spacetime models. It's like building a new kind of map where roads don't bend, but your compass twists. Before the expanding universe model was widely accepted, some physicists, including Zwicky, suggested redshift came from photons tiring as they traveled vast distances. Einstein considered this as a way to avoid abandoning his static universe, but found the explanation lacked sufficient physical mechanisms. The theory couldn't account for observational data such as cosmic background radiation or time dilation in supernovae. Eventually, Einstein accepted cosmic expansion, calling the cosmological constant his biggest blunder. Tired light was discarded as data overwhelmingly favored the Big Bang model. Einstein briefly entertained tired light to avoid modifying general relativity, but ultimately sided with dynamic cosmology. It's like thinking a flashlight gets dimmer, not because of distance, but because the beam gets sleepy. Einstein was one of the few physicists to support deterministic alternatives to the Copenhagen interpretation of quantum mechanics. He engaged seriously with de Broglie's pilot wave theory, believing that quantum randomness masked an underlying reality. Though he never published a complete alternative, his concerns shaped later developments like Bohmian mechanics. Einstein maintained that any satisfactory theory must preserve causality and locality, even if hidden. His EPR paradox in 1935 sparked debates still central to quantum foundations. Einstein wrote favorably of de Broglie's guiding wave concept and praised Bohm's 1952 revival, despite reservations about non-locality. It's like believing that magic dice don't roll randomly. They just have secrets we can't yet decode. Einstein occasionally corresponded with spiritualists, vitalists, and metaphysical thinkers, proposing cosmic life energies like prana or chi. While he remained courteous, he insisted that science must remain empirical and falsifiable. He saw such ideas as philosophically or culturally interesting, but scientifically empty without measurable effects. Unlike Reich's Orgone energy, these claims were never experimentally tested by Einstein. His letters show a sharp boundary between intellectual openness and empirical standards. In exchanges with spiritualist figures like Tagore and Bergson, Einstein emphasized that physical laws cannot depend on subjective or mystical interpretations. It's like respecting poetry as metaphor but refusing to use it as a physics equation.